Welcome, everyone, to our fourth and final seminar in the series. Tonight, we are looking at feedback loops and tipping points. So as a quick refresher, in our previous episode, we saw how carbon moves around the Earth. We were looking at the carbon cycle. And we described how carbon flows between different stocks. And that concept of stock and flow is going to be the foundation on which we continue to build our understanding. So let's take a quick look back at this picture of the carbon cycle on our planet. Again, numbers in white are carbon stocks. They are stores or amounts of carbon that are present in various locations around the Earth. These numbers are measured in gigatons of carbon. The numbers in yellow are flows of carbon, measured in gigatons of carbon per year. For example, the process of photosynthesis, were it not for human activities, would move about 120 gigatons of carbon from the atmosphere into the plants. And then between plant respiration and microbial processes, 120 gigatons of carbon would move back from the plants into the atmosphere. However, numbers in red are additional flows of carbon due to human activities. So we are directly putting about these days more like 9.5 gigatons of carbon into the atmosphere per year, some of which is being taken up by increased plant growth and increased gas exchange between the air and the ocean. So tonight's talk is going to have 4 key parts. In the first part, we will define feedback, examples of which we have already seen in last week's seminar. In the second part, we will define equilibrium, an understanding, a concept that will arise out of our examination of feedback. In the third part, we will define tipping points, a concept that will arise out of our examination of equilibrium. And finally, we will bring tonight's seminar and the series to a conclusion. So let's begin with feedback. Feedback occurs whenever the amount of flow depends on the amount of stock. We talked about stocks and flows of carbon. There are stocks and flows of many quantities that are relevant to the Earth's climate. Let's look at the water in a bathtub. This is a classic example in climate modeling as an introduction to the concept of stock, flow, and feedback. If I have a bathtub that is partially full of water, I call that my stock. However much water is in the bathtub, say 10 gallons, right, is how much stock of water I have in the bathtub. There's an inflow of water because the faucet is on and running. Let's say it's 1 gallon per minute. And I have maybe some outflow, the water is draining, right? If that's also 1 gallon per minute, then I have a balanced flow. I alluded to this kind of balanced inflow and outflow with an earlier example of apples, right? If I buy and eat 1 apple per day, then I will not have an overabundance of apples, nor will I run out of apples. In this particular example, let's make it even a little bit more detailed. Let's say that the outflow of water is driven by the weight of the water in the tub. The more water there is in the tub, the harder it's going to push on the water at the bottom, and the faster the water will flow out. Therefore, the rate at which the water leaves the tub depends on how much water is already in the tub. If the tub is full, the outflow will be larger than the inflow, and the water level of the tub will drop. There will be less water in the tub. However, if the tub is nearly empty, the inflow, which we're presuming is staying constant here, will be larger than the outflow, and the water level will rise. So this is an example of feedback, right? The rate at which the water leaves the tub depends on how much water is already in the tub, which in turn influences how much water will be in the tub in the next moment. This is also an example of a concept called path dependence, where I could have the tub being exactly half full because the water level is dropping down past half full, or I could have the tub being half full because the water level is rising up to half full. The system could be in 2 different states, but there's more than one way to get to that state. We'll come back to that sort of concept in a little bit. Many other states of the system are possible. If the inflow is greater than the outflow, the tub will overflow. And this sort of thing is what might happen to Earth's energy budget unless we humans continue to take strong actions to alter our alterations, to alter our carbon emissions, right? The Earth is absorbing a certain amount of energy. Right now, it's absorbing more energy than it used to absorb. And eventually, the Earth will increase its temperature and radiate more energy. Overflowing is just another way of saying the outflow is going to increase, but perhaps in a not so desirable way. So that's a possible state of my tub system. Or if the outflow is greater than the inflow, the tub will remain nearly empty. I couldn't think of a good analogy for this one. But of course, what we probably want is for the outflow to be equal to the inflow, right? Then the level of water in the tub will remain constant. If I take in 1 gallon a minute and I outflow 1 gallon a minute, then however much water I have, I'm going to stay there, right? So we would say that this is an equilibrium state. This is an equilibrium state. And by equilibrium state, we mean a state of the system that is not going to change over time. I could leave this running for an hour and be confident that I would not come back to a flooded bathroom. Before we go on to defining equilibrium properly, let's look at some examples of feedback. Well, I say that. Some of these are examples of feedback, I think, and some of them are not. So let's go interactive. Which of these are examples of feedback and which are not? Example number 1. The population of a prey species declines. This causes the population of the predator species to decline as well. With fewer predators, the prey population rises. Raise your hand if you think this is an example of feedback. 1, 2, 3, and of course people with their cameras off. But yes, you're all correct. This is an example of feedback. This is an example of feedback because the prey population depends on the predator population. In other words, the stock depends on the flow. Okay, example number 2. A man goes on a diet by reducing his food intake. He loses weight at a steady, sustainable rate. Raise your hand if you think this is an example of feedback. Tahila says no, and she is correct. This is not an example of feedback. His weight does not depend on. This isn't cycling back on itself, right? He is directly controlling his food intake. His food intake. I suppose you could maybe make a psychological argument that his food intake depends on his weight, but this is not an example of feedback. Example number 3. A new jet plane is tested. When the pilot adds more fuel, the plane flies faster. When she reduces the fuel, the plane slows down. Raise your hand if you think this is an example of feedback. Good. It's not, right? This is not an example of feedback, right? So these guys are not examples. 2 and 3 are not examples of feedback. Let's look at the next one. Example number 4. As the Earth warms, more of its ice melts during the summer months. With less shiny white ice, the Earth reflects less solar radiation into space, absorbing that radiation instead. This results in the Earth warming even more. Is this an example of feedback? Yes. Yes, it is. So this is an example of feedback because the stock of ice depends on the flow, on the change in the amount of ice. And apparently PowerPoint has decided the font size needed to be really small. So let's see if we can't make that a bit bigger.
Make your text box bigger.
Yeah, that's just what I was going to do. There it is. All right. So 2 of these were examples of feedback and 2 of them were not. But we were talking about equilibrium, right? An equilibrium state is a state that doesn't change over time. So we're led to our second key concept, equilibrium. When a system is in a state that does not change over time, we say that this is an equilibrium state. It's worth noting that there can be a sort of dynamic equilibrium, right? There's many kinds of equilibrium. Dynamic equilibrium is the idea that the system is sort of in a steady cycle, right? Things are going back and forth or round and round in the same way every time. And actually, the bathtub is a really good example of this. The system is in an equilibrium state, but water continues to move, right? It's just that I happen to be removing as much water as I'm taking in. And so this is an example of a dynamic equilibrium. Somebody could come and really open up the faucet, right? And that would be disturbing the equilibrium state, taking it out of equilibrium. Or somebody could come up and shut off the water. And if they shut off the water and close the drain, then that would put it into a different equilibrium state. So there's multiple kinds of equilibrium. But first, here's a nice picture. Anyway, so here's a classic case study in equilibrium. First, I put a ball inside a bowl, and it stays there. In fact, this is very stable. If I give the ball a nudge, then gravity will pull the ball back down to the center of the bowl. So we call this a stable equilibrium. And I'm going to introduce some other vocabulary in a minute. But if I turn the ball upside down, and I'm very, very careful about this, I can rest the ball on top of the inverted bowl. And here it's not so stable. If I give the ball a nudge, gravity instead takes the ball very far away from where it was before. So in the case of the ball inside the bowl, if I give it a nudge and push it up the sidewall, the ball will return to its starting position. The forces which influence the motion of the ball, gravity in this case, act against my nudge. And so we call this a stabilizing feedback. The feedback process returns the system to its original state. Stabilizing feedback, or stable equilibrium, if you like. Over here, if I nudge the ball on the inverted bowl, it falls off the bowl entirely. The forces which influence the motion of the ball act with the nudge. And so this is called an amplifying feedback. Whatever your nudge is, the natural forces in play are going to amplify that effect and make it bigger and bigger. So this is an amplifying feedback. And we're going to look at multiple examples of feedback in Earth's climate and decide whether they are amplifying or stabilizing. So here's one we've seen already. The population of a prey species declines. This causes the population of the predator species to decline as well. With fewer predators, the prey population rises. Is this an amplifying feedback or a stabilizing feedback? Michael?
Stabilizing.
It's a stabilizing feedback because the prey population returns to where it was before, right? And we can represent that with a flow chart. Although I realize I should have separated 1 and 2. But here it is, right? Pay no attention to the flow chart at the bottom, right? We can see I start with reduced prey, which leads to reduced predators, which leads to increased prey, which I suppose leads to increased predators, which then leads to reduced prey again. This is a stable feedback loop. We'll repeat endlessly unless something comes along and disturbs it. Humans. So let's look at the second example. As the Earth warms, we saw this one already as well. These are our 2 feedback loops from the first example slides that I had. As the Earth warms, more of its ice melts during the summer months. With less shiny white ice, the Earth reflects less solar radiation into space, absorbing it instead. This results in the Earth warming even more. Amplifying or stabilizing?
Amplifying.
This one's an amplifying loop. Right. We start with increased temperature, which leads to more ice melting, which leads to less light being reflected, which leads to more heat being absorbed, which leads to increased temperature, right? So I've it's still a cyclical diagram, but I'm definitely increasing things as I go, right? This is not returning to its original state, but rather returning to a different, higher temperature than what it had. Is this making sense? Does anybody have any questions? Tahila.
Mute. Okay, unmute myself. Yeah, so I think one of the mistakes that I made is I was looking at equilibrium as stabilizing equilibrium. When you gave the example, because number 4 I got wrong, and to me, so the amplifying one, which I saw this as amplifying, but if it's amplifying, I didn't see that as a form of equilibrium.
It's not. So one of these two examples is in a state of equilibrium, the first one.
Right.
But this one is going to move out of equilibrium. It's going to be a change in the system over time.
But how can you have amplifying equilibrium? Like
it's not. It's amplifying feedback. Did I say amplifying equilibrium?
Okay. That's my mistake. Okay.
This is an amplifying feedback, right? Okay. Where the amount of ice depends on how it happened before, but it's the overflow kind of feedback rather than a stable equilibrium kind of feedback.
Yeah, that's why I got confused.
I'm throwing a lot of new vocab around, so that's understandable, right? So just to recap, the example with the prey and the predator populations is an example of equilibrium because it's a sort of a dynamic equilibrium where the system oscillates through multiple substates but always returns to its original state, meaning an original number of prey species members. Whereas the example with the ice melting is not equilibrium, but it is an example of feedback, right? So it might help to go back here where I have lots of different examples of the bathtub state, but only this slide showed an equilibrium. So I can have the bathtub out of equilibrium, or I could have to have the bathtub be in equilibrium, even though both of these have feedback happening. Okay, so let's go on to our next set of examples. Examples 3 and 4. So example number 3 we saw last week, the weathering reaction, right? The weathering reaction, where if there's CO2 in the atmosphere, then some of the CO2 will get absorbed by the rain will fall, the CO2 will react with certain rocks and form sedimentary rocks, which will then get washed out to sea, removing the CO2 from the atmosphere. So we saw what would happen. We thought last week about what would happen if there was excess CO2 in the atmosphere. So that would make the weathering reaction happen faster, which would then remove CO2 from the atmosphere a little bit faster. So is this an amplifying feedback or a stabilizing feedback?
Stabilizing.
This is a stabilizing feedback, right? We gave the Earth a nudge by putting more CO2 into the atmosphere, and the natural process has an effect of acting against that nudge, right? So this is a stabilizing feedback. It's not as strong or as fast as we would like it to be, but it is stabilizing. Here's another one. As more CO2 is added to the Earth's atmosphere, the temperature increases. This causes the growth rate of plants to increase. You know, plants like a warm, humid environment, or at least some plants do. More plant growth will use more CO2, removing it from the atmosphere. Amplifying or stabilizing?
Stabilizing also.
Also stabilizing. Here are the flow charts for that one, right? So both of these are stabilizing feedbacks for the same reason, which is to say that the natural process is to act against the increase in CO2, right? Again, neither of these are as strong or as fast or as robust as we would like them to be, but they are helping a little bit. In the case of the weathering reaction, a very, very little bit. The plant growth is helping us out more. The plant growth is actually this +3 on the image. It's this one, right? That is that reaction, so far as I know. The increase in photosynthesis because of the increase in CO2 in the atmosphere. All right, 2 more sets of examples. Let's see. I guess I already did the flowchart on this one. So let's do 5 and 6 together. An increase in atmospheric CO2 causes the ocean to warm up. The warmer waters are less able to keep CO2 dissolved, so some CO2 outgasses into the atmosphere. Is this an amplifying feedback or a stabilizing feedback?
Amplifying.
This is amplifying, right? In fact, let's just take this flowchart down here and move it up and make the new flowchart. So we start with increased CO2. This results in warmer ocean temperatures, which means less CO2 dissolved in ocean. Just leave it as dissolved, which finally means outgassing CO2 into atmosphere. Sphere fits, right? So this is an amplifying feedback, right? We pump a little extra CO2 into the atmosphere, it's going to pump it right back out at us, right? So this is an amplifying feedback. I don't know that this is exactly reflected on the image we saw before, which showed an increase in the uptake of CO2 from atmosphere to ocean. But I did get this from actual climate scientists, so I believe that this is a valid process. This process might be happening, but overwhelmed by other feedback processes that are causing more absorption of CO2 by the atmosphere. One of the key ideas of today's lesson is that to describe climate processes involves multiple overlapping feedback loops. And finally, this one I've already got written out here. An increase in atmospheric CO2 causes plants in the Amazon rainforest to open their pores less widely, right? So this is just a thing that I learned about plants very recently, especially the plants in the Amazon rainforest. If there's an increase in CO2 in the atmosphere, the plants will not open their pores quite so much. And when they don't open their pores quite so much, they evaporate or transpirate as much moisture into the air. And with less water going into the air, the Amazon rainforest, the atmosphere right around the Amazon, over and around the Amazon rainforest becomes drier. And that means there's less rainfall, and that means the environment is less suitable for the growth of tropical plants, such as one typically finds in the Amazon rainforest, which means there's even fewer plants opening their pores to evaporate water, and so on. In a way, the Amazon rainforest was already a stabilizing feedback loop at equilibrium, right? At a dynamic equilibrium, right? The plants would absorb and circulate the water, which would provide an environment with a lot of water, which would facilitate the growth of more plants like those plants, which would then circulate the water, right? And so the Amazon rainforest itself is currently a stable feedback loop at a dynamic equilibrium. But there's an amplifying feedback loop that is threatening to disrupt that stable equilibrium, which is namely the increased CO2. With increased CO2, the plants evapotranspirate less water back into the air above them, so there's less rainfall, so there's less growth of tropical plants, and so less CO2 is absorbed by the plants, and there's more CO2 in the atmosphere. Lather, rinse, repeat. So this one that I've diagrammed here is an amplifying feedback because there's less absorption of CO2 by the plants. Now, this is a particularly interesting one because if this were to keep happening, if this particular amplifying feedback loop were to become stronger, then it could result in a sort of collapse of the previously self-sustaining Amazon rainforest stable feedback loop, right? You could get a large sudden die-off of tropical plants and tropical forest in the Amazon, and that environment would start to become more like a savanna. Lots of grasses, very few trees. Michael.
I think you're taking that, like you said, it's something new for you. So I don't know how knowledgeable or deeply knowledgeable you are on it, but it seems like if this is happening, it's probably not a massive effect that it's going to turn you're going to show me I'm wrong, but it's not, I don't know if it's necessarily going to turn the entire Amazon into a savanna as opposed to being
it might not be the entire Amazon, but it would be significant. I'm jumping ahead in my slides. There is a disclaimer, which is that this is not happening yet.
To some degree, you don't think it's happening to some degree?
It's probably happening to some degree just because humans are directly deforesting the Amazon.
And logging and all the other stuff that's going on.
Yeah, that's worse than it's probably worse for the Amazon than all the CO2 buildup. In other words,
correct. At the moment, the direct human logging is worse for the Amazon than this dieback feedback loop. But what I'm getting at here is that if we let the warming continue, this could become very strong, and there could, hypothetically, come a point where the Amazon feedback loop itself collapses.
I would even say if it's a slow effect, which it undoubtedly is, I would actually think that Darwin would cure it for us, meaning the plants that die because of the extra or don't do as well because of the extra CO2 make room for the ones that are okay with it. And
that's true. And that would be the savanna-like environment.
I don't know if it's necessarily savanna. It could still be a rainforest. It's just different plants in the rain or different proportion of plants in the rainforest than we have now.
That could be. I'm not enough of an expert on rapid elements of evolution to argue that point. What I am trying to do is use this as an example of a tipping point, where it is possible that the increased CO2 in the atmosphere could lead to a sudden and very difficult to reverse change in the way the Amazon rainforest functions or even exists. There are other examples like this, where here's a much simpler example. We know that by putting more CO2 into the atmosphere, we are increasing the temperature of the planet, including and perhaps in some way, especially at the polar ends of the planet. If the temperature of the ice shelves gets warm enough, the ice shelf will collapse and melt into the ocean. If at that very moment we shut down all CO2 emissions, the ice shelf is not going to spontaneously refreeze and climb back onto the land mass, right? What's done is done. This is a tipping point, right? A tipping point is when a system makes an abrupt change from one equilibrium state to another equilibrium state. We actually saw examples of this already with the ball and the bowl. The ball resting on the inverted bowl is in an equilibrium state. And I come along and I exert what's called in the climate lingo a forcing. In this case, I exert an actual force on the ball. I give it a nudge, right? And if I give it enough of a nudge, the ball will fall off the bowl. It will go from one equilibrium state at rest atop the inverted bowl to a new equilibrium state at rest on the table next to the bowl, or maybe even on the floor. And even if I stop pushing at that point, the ball is not going to go back up to where it was. I have to do something different to get the ball back up to where it was. Right? So this is an equilibrium state for the ball, but so is this. Right? So if I go from one equilibrium state to another, that's a tipping point. You might also liken it to the concept of a phase change in chemistry and physics, right? A sudden, very difficult to reverse change of state of the system. Well, it's a little bit easier in chemistry. We just have to refreeze the thing. But we're talking about slightly more complicated systems. So that's an example of a tipping point. Before we go on to, before we talk about the concept more, I want to talk about the origin of the phrase tipping point, but go ahead, Michael.
So I just had a question, since you gave the example of the ice shelf, falling off. If temperatures around the world go up, as they have,
Yep.
presumably more water gets evaporated off the ocean. So there's more water vapor in the air, I'm guessing. And that's one of the reasons why I asked you this question at the end of last week's class, about water vapor percentage in the air. And I assume that becomes essentially also a feedback loop, because water vapor is a greenhouse gas as well, as we saw.
Yeah.
So is that also part of the tipping point, if you will, or the cycling that heats up the world?
I can't recall off the top of my head if direct evaporation of the oceans, I don't recall that getting mentioned in the materials I've been learning from. Although it does seem like something that would happen. Therefore, my first instinct, which is not an answer I'm super confident about, is to say that it is happening, but it's very small compared to some of these other effects. I would have to do some more research and get back to you on that, I think.
Okay.
I didn't do the homework you gave me. Slipped my mind. However, I can still do that and get back to you through email or something.
Okay.
All right. Let's talk about the origins of the phrase tipping point. This is something else I didn't know about until I was doing my due diligence and checking my sources for today's presentation. This picture here is a screenshot from an article on Merriam-Webster that says, this part of the article says, when tipping point first began to be employed in general use, it was almost entirely in reference to the propensity of white families to move out of an area when a certain percentage of the neighborhood was composed of black families. It served as a precursor of sorts to the phenomenon of white flight. And they give a couple of contemporary quotes here, both of which happen to be from 1959. They had two others as well, which I'm sure even those four were just a limited sampling of their indexing. But there are a great many contemporary quotes referring to tipping points of white acceptance, right? Or the percentage of minority occupancy that initiates a withdrawal of other tenants has been denominated the tipping point. So I think it's important to recognize this, because this very phenomenon of economic segregation of neighborhoods leads to another climate phenomenon, which is to say redlining. Redlining was the socioeconomic practice of outlining minority and predominantly African American neighborhoods in red on the map. But today, even though redlining is nominatively banned, the historically redlined neighborhoods are experiencing climate change differently than non-redlined neighborhoods. So this was a report about what's going on in Yonkers. This article came out just last summer, July 2020, from an organization called Groundwork Hudson Valley. And you can see this is a map of Yonkers, and these red shaded neighborhoods are historically redlined. And because of their redlining, they have more concrete and asphalt and less greenery. And this results in them experiencing even greater temperature changes than other neighborhoods that did not experience this. So redlining, in fact, and I'm sorry to say this, is just one example of how climate change is disproportionately affecting people of color. However,
I wouldn't say that's climate change. I would just say that's, in other words, if you had built a neighborhood with the same proportion of asphalt and grass and whatever 100 years ago, when we didn't have all the extra CO2 and the climate hadn't yet changed, you'd have the same effect. Climate change. It's
there would
just
certainly be
it's
more.
composition.
Would certainly be more of a heat island in that place. But my understanding is that it scales. So if the global average temperature goes up half a degree, neighborhoods like this will go up even more than that. and that's why it's disproportionate. But there's good news on the local front. The rest of the article talks about solutions. The Municipal Housing Authority of Yonkers, which houses thousands of low and moderate income families in the affected areas, said that they will work to fix the issue at its properties, including providing cooling centers in preparation for blackouts. The agency also wants to use reflective paint for roofing at public housing and increase the tree canopy in hotter neighborhoods. This is not a seminar about solutions to climate change, of which there are many, but the central lesson of a seminar series about solutions to climate change is that there have to be many. In particular, we have to think locally and globally, sometimes both at the same time. And so local solutions like this one are an integral part of how we should be dealing with climate change. But back to tipping points.
If you
Unless
have any,
Michael,
if you have any sway with these guys, tell them to put solar panels on the roof instead, and that way they can reduce the power cost of the people living in the buildings.
But, and I would have to do the math on this, and I am hopefully they're already doing the math on this. Just by using reflective paint, you might reduce the power cost because you won't have to run HVAC so much. So it might even out or even be better with just the reflective paint.
The solar panels will probably block, most of the radiation hitting the roof because they're raised. There's an air gap between the panel and the roof.
Right.
And the panel's absorbing a lot of the radiation. I mean, that's the whole point of the panel.
Yeah, I mean, maybe, for example, what's one thing that's been going around in the news lately is this idea in California to put solar panels over the canals. And this would not only generate some electricity from the sunlight, but it would also reduce the evaporation from the canals. So who knows? Maybe something like that would be good.
Fish farms occasionally will have panels over the fish farm to keep the fish farm cool. Mm-hmm. And generate power that's needed to operate it.
Yeah. So who knows? Maybe they're considering something like that. So let's go back to a more general definition of tipping points. I love this particular example, which is chocolate, right? So when you buy a bar of chocolate, the manufacturer of that bar of chocolate has used a special and highly delicate process called tempering, where they carefully control how the chocolate cools after it's made to ensure that the chocolate enters what I'm going to very scientifically describe as a desirable equilibrium state, right? Which is to say it's got just the right crystalline formation so that it's smooth and shiny, it melts in your mouth and not in your hand, right? It's delicious. However, if you then take that same bar of chocolate and go over it with, for example, a hairdryer, you will at least partially melt the chocolate, and then you let it re-solidify. It's still a solid bar of chocolate. It is no less delicious, except that, well, maybe its texture is changed and it melts more easily, right? So no, it's not as shiny anymore, right? So it's still chocolate, but it's different, right? And crucially, even though the temperature of the chocolate returned to its initial value, right? It's still at room temperature now that I'm done with the hairdryer. The chocolate didn't return to its original crystalline state. The molecules of the chocolate are in a different arrangement now. So this is an example of a tipping point, a sudden change between two equilibrium states of a system.
What's CA?
Oh, I think she's using that. The source I got this from is using that to mean about, melts at circa or about 28 degrees Celsius. Yeah. Okay. Yeah, that's fair. That was not obvious. So that's tipping points in chocolate. Let's look at tipping points in the Earth's climate. And I could think of nothing better. I couldn't think of anything to add to this picture myself, so I just made it the whole slide. This is from an organization called Carbon Brief. Although I will point out that the IPCC, or Intergovernmental Panel on Climate Change reports, also talk about tipping points. This is a distillation of some of what's talked about in the IPCC report, or one of them anyway. So we talked already about this one that's called Amazon Rainforest Dieback. And as we said, fortunately, the evidence that this tipping point is already happening is minimal. Hopefully, it won't happen. Hopefully, we will successfully change what humans are doing with enough time and temperature to spare so that this never occurs. But it might if the world gets to about 3 or 4 degrees of warming. Other ones you might hear about, I see this one in the news a bunch, the Atlantic Meridional Overturning Circulation, or AMOC, right? So the AMOC, or Atlantic Meridional Overturning Circulation, is an ocean current. Oh yes, Michael found the article that I got this from, right? Hopefully, is it really easier to see there than on my slide? I can zoom in.
Yeah, well, it just because I can zoom in.
Yeah, fair enough. So this is an ocean current that cycles warm water around the Atlantic. And this is one of the reasons why a lot of Europe has a nice warm temperate climate when it's really as far north as Canada, right? And unfortunately, there's a little bit of evidence that the AMOC is already weakening. One of the reasons why it's weakening, or I think the main reason why it's weakening, is that as Arctic ice melts, you have an increased influx of fresh water into the circulation of the AMOC. And that is going to behave differently than the salt water that is typically in the AMOC. So because of an increased influx of fresh water, the AMOC has already weakened by 10 or 15% compared to pre-industrial levels. If the AMOC shuts down, remember this is one dynamic equilibrium, right? This is like the bathtub that's got inflow matching the outflow. If this goes to a different equilibrium state where the circulation just shuts off, then Europe is going to get a whole lot colder. And that would be very, very bad for a number of reasons. Other ones that are listed here, Greenland ice sheet disintegration or permafrost loss. So these two are of a kind, right? This is once you melt it, it's very hard to refreeze it. Kind of a tipping point, right? Once you melt it, stopping your CO2 emissions are not going to make the ice climb back up on the shelf and refreeze itself. Permafrost is in a way even worse because when the permafrost, if the permafrost melts, then it will itself also release more CO2 and methane that was stored in that frozen soil. So if the permafrost has substantial melting or thawing, then we could be dealing with even more amplified warming. Boreal forest shift. A shift in boreal forests seeing expansion into tundra in the north and dieback to the south, right? Regional warming and ecological shifts, right? If the world gets warmer, then the same kind of dieback could happen in the southern region, and the forests would start to move into tundra in the northern region. What do we have here? Oh, circulation changes down at the bottom. So other circulation changes like the AMOC, the West African monsoon shift, and the Indian monsoon shift. We are near the end of our seminar. Before I go to my conclusion, does anybody have any questions about these tipping points? Okay, let's go to the conclusion, and I think that'll help us all process what we're looking at here. So, conclusion. In which we wrap up our whirlwind tour of Earth's climate and look to the future. Some of you, and thank you to those of you who have stuck with me these 4 sessions, have learned a lot about Earth's climate and might be feeling a general sensation of, well, what do I do now? What now? Well, the first thing I want to tell you is don't panic. All right? It's very easy to conclude that all is lost, that the Earth's climate is doomed, that there's nothing else we can do. I don't want you to think these thoughts, right? Stamp these thoughts out whenever you can. Realize that there are still things we can do. It's almost refreshing in a way to think, hey, we got ourselves into this mess. We can get ourselves out of it. This, I think, is the last tipping point that I want to talk about. Us, right? If we can communicate with each other and communicate with the powers that be, more on that in a second, we can create a tipping point in the way human beings run our civilization. and we can stop this thing in its tracks, right? So you're thinking, okay, what do I do now? If you're thinking, I feel galvanized to action, you need to do something about this. Well, remember that most of the human activities that are causing climate change are institutional in nature, not caused by the choices that you make as an individual, but by the choices you are offered by governments and corporations. And in fact, most of the climate emissions that are causing this problem are caused by only the very largest corporations. So pound for pound, the most effective thing you can do as an individual is to send messages to your elected representatives that ask for climate solutions. Voting with your dollar is also a good choice. If your reaction to all of this is, I need to learn more, I don't know enough about this, where do I start? Well, these are the 2 courses I took last year when I was getting this material seriously in gear. Modeling Climate Change by David Archer on edX, and Climate Change, the Science by Sarah E. Harris, also on edX. They are professors, respectively, at the University of Chicago and the University of British Columbia. I found their material clear and yet detailed. I think those are excellent places to start. Of course, as I say, there are many other wonderful online courses out there. A simple search for climate change on edX brings up a dozen results. So find one that works for you. What am I going to do next? I'm going to continue teaching the physics of climate change to my students and in any other seminars or platforms I can manage. I am thinking about this, though. If SAR gives me another seminar series next year, I might focus it on solutions to the climate change. If you're interested in learning about that, I suggest you look up Project Drawdown, which is a website and a book that lists about 100 solutions to climate change, with the intention that we should be doing all of them. So that's it. Thanks, everyone, for coming. If you have questions for me, I'm happy to talk with you further.
Well, thank you. This was great.
Thank you. Oh. Lisa, I'm not sure if you're saying something, but I'm just getting a lot of static.
We're all getting it.
Yeah, nope.
Bathtub is overflowing.
Yes,
Bathtub.
that's an example of audio feedback. Lisa, perhaps if you type your message into the chat, I could read it there.
I actually have a question.
Go ahead, Michael.
If we jump back a number of years, I'll say jumping back to Al Gore.
Oh, thank you, Lisa.
Al
Yes.
Gore and others were, pretty serious about this early on.
Yep.
But they also were kind of quoting gloom and doom with timeframes that have since passed. In other words, he was pushing the quote unquote hockey stick model and things like that, essentially saying the tipping points were all hit and we're going to see rapid change and all these horrible things are going to happen. And yes, we're still seeing temperatures going up, but a lot of the at least horrible things that they were calling for didn't happen. And I can send you an article from 1995 that said that we're going to lose all of our coastlines in the U.S. in 25 years, which is now.
Right. Certainly, some of that has happened to some extent. Right. Certainly not all of the.
They were saying all.
Right. So granted, that didn't happen, or at least didn't happen by this time. I will say, in my experience studying this, and in general, whatever my PhD in physics is worth, as somebody who understands the evolution of systems over time, solving the time question is the hardest thing you can ask in climate change. And that's because, as we've seen today, there are so many feedback loops. These were just a handful of examples. There's feedback loops at all different scales, from the from the habitat of one single ladybug all the way up to the entire Amazon rainforest, all the way up to the entire planet. There are feedback loops overlapping, mixing, interfering with each other. It's crazy. So asking when something is going to happen is hard unless you're talking about the broadest variables like global average surface temperature. And then we can get a reasonable estimate, right? So I don't 100% fault. I don't know. I confess I never watched An Inconvenient Truth, right? I don't know what timetables he gave. I do think that if they were being super confident in time estimates about things like coastline change, then they were being a little bit sloppy with the science. And I say this, what do I mean by that? I mean that science encourages us to say, I don't know yet. We just don't have the evidence to come to a conclusion on that question yet. Right? Science encourages patience when you don't know the answer, and that's hard to do. Right? We want clear answers in our lives, and this is I would say the hardest problem humanity has ever faced. Not just a hard problem, but the hard problem. As far as there was another thing I was going to say, but I forgot. It's much easier to say what will happen than it is to say when it will happen. Right now, I would say in my experience, doing as much reading as I can, what actual climate scientists are trying to do is mitigate the worst of the outcomes, say 50 to 100 years from now. And that starts with stopping the trend today. So it's I used to tell my students when I was teaching at the college level, I would do little bits and bobs of climate change. And I used to tell them climate change is not a far in the future somewhere else problem. Climate change is a here and now problem. Well, the reality is it's both. And if we want to solve one, we got to start by solving the other. That's my take on the matter.
I really, the thing that's always resonated for me is things like carbon credits, where you essentially create an economic incentive.
Yeah,
to
I think that
carbon.
has a place. As I said, I think we need to use all the solutions we can think of. Carbon credits.
That will then drive all sorts of alternative energy and things like that.
Cap and trade, government subsidies for this and that, ending government subsidies for fossil fuel industries, creating government subsidies for renewable energies, right? Direct investments, investing in education, regulations on pollution, all of it, plus 100 other things that I didn't think of off the top of my head. All of it working together. That's how we solve this.
And the other, what I see as unfortunately a problem is you have, a few billion people on the planet who are going up the industrial curve, and it's much easier and cheaper for them to build a coal plant than to do something that's green.
Yeah. I mean, if you look at how much coal, oil, natural gas reserves are still in the ground, and yet the companies in question have already bought and sold the futures on those reserves, we're going to have to pay them to keep it in the ground.
Well, I'm not even talking about that. I'm talking about, China, India, Africa, that are burning things because it's cheaper to burn things than to do other energy generation. And they have energy generation or need energy usage curves that are going up geometrically.
I want to say you're wrong. I wish you were wrong. I think you're right.
Unfortunately.
That was wishful thinking on my part. Yeah, I don't know. As I said, it's going to require global, national, regional, local solutions, all of them working together. I don't know what's going to be right for a town in India or a region or a county or a state within India. I hope they're going to do the right thing soon and maybe figure out a different way to meet their energy needs.
Okay, but we start with ourselves.
Yes, so we here in the United States have to start with us. Yes, absolutely. I'm not losing sleep over what what the people in China are doing. I'm losing sleep over the fact that my high school that I work for has recycling bins, but just puts it all in the same dumpster and sends it to the landfill. Yeah,
Seriously?
seriously. I'm working on it with the environmental club. It's a
My,
work in
my, my
progress.
school does the same thing.
Yes.
Yeah,
Um, yeah, imagine that. It's almost like we work at the same school.
almost.
Huh. Now
So
I have to check what my building I live in is doing because we
think
separate out
the
everything.
old phrase of think globally, act locally starts to carry real meaning when you're talking about problems like that.
Okay.
That said, I'm also kind of worried about what China is doing because the quote unquote market, for lack of a better word, for plastic recycling in the United States had the bottom fall out of it a couple of years ago when China stopped accepting low grade plastics.
Mhm.
That's where that's where it was going, and China said, "Nah, we don't want it anymore." And so now a lot of municipalities in the United States are going, "What do we do with it?" Uh, it's not an easy question, right? So there's a local so just looking at where I am, right, my life or anyone else who's working at SAR, I guess, there's a very very local problem, which is we have these illusory recycling bins, right, to the point where I'm taking my recycling home to my apartment complex instead of leaving it at school, right?
Right.
There's the the state level or the city level question, which is what is the city doing with the plastic that we give it, or the paper, or the cardboard, or the metal, right? Then there's the national question of like, what is the federal government, if anything, going to do about our recycling issue? Well, right now the federal government has bigger problems. So, okay, fine. What's China doing with plastic, right? So there's all this all linked together in feedback cycles.
Okay.
All right.
I think that's a great place to end it. Thank you all for coming.
Take care, everybody. Thank you.
Thank you very much.
Signing off.